we go. So we're going to talk about the determination of solubility product of an ionic compound. This is a fairly simple lab. There's not a ton to it. I got to be honest, I haven't really even looked at the pre-lab for this yet. But I mean, it should be fairly straightforward. So it's basically talking about the solubility product constant and where it comes from. And again, you just got to kind of watch the stoichiometry here because this is 2Cl. Then in the Ksp expression, it's going to be Cl squared. So you just have to watch out for things like that. In this experiment, we're going to use calcium and hydroxide ions. So it's going to form calcium hydroxide, which is, again, it's not going to have a one-to-one stoichiometry, so we got to watch out for that. So the example they're giving you in the pre-lab questions is silver chromate, AgCrO4, which I think we've actually done that example in class. So if you're going to write the solubility product expression, I think you guys can do that. I don't think I need to help you out with that at all. Again, just watch the stoichiometry there. Number 2, if one has a solution of 0.10 molar silver nitrate and is diluted by a factor of 2, what is the new concentration? Okay, that's very easy. Just want to make sure that it was as easy as I thought it was. If you have a 0.1 molar solution and you dilute it by a factor of 2, in other words, you're basically doubling the volume, so you're having the concentration. So the new concentration, of course, is going to be 0.050 molar. Okay, and that one might trip you up just because it is so easy. The dilution by a factor of 2 is carried out 5 times. Okay, so now we have to think about, you can do this one of two ways. You can just sort of think it out, or you can use math. I mean, either way, you're going to have to use math, but so after the first, I need more room. So after the first dilution, we've got 0.10 molar. Diluting it the first time, it's going to be 0.050 molar. Dilute it again, it's going to be 0.025 molar, and so on and so forth. So you can do it that way if you want to, and just keep having it until you've done the dilution 5 times. The other thing you can do on this one is you can actually, because it's going to cut in half 5 times, you can take 1/2 to the 5th power, or 0.5 to the 5th power, and then multiply that by the original concentration, which is 0.1, and that should give you a new concentration of 3.125 times 10 to the negative 3rd, which 3.1, I guess, would be our concentration. Molar on that one. Okay. And again, that's the same answer that you should get if you do it the first way that I showed you there as well. Let's see. Value of Ksp for silver chromate is reported to be 1.1 times 10 to the negative 12th. In a saturated solution of silver chromate, the silver ion concentration is found to be 2.5 times 10 to the negative, I think that's a 4. Let me look at the actual lab here to make sure, because I can't read that number. Okay, here we are. Yeah, times 10 to the negative 4th. Okay, so the Ksp is 1.1 times 10 to the negative 12th. Silver ion concentration is 2.5 times 10 to the negative 4th. What must the chromate ion concentration be? And then it says you have to show your work on that one. So when we do that, sorry. We're just going to have to set up the equation here. And so if you write out your equation, well, actually the equation's already written up here, so then we write our Ksp expression for this. It's going to be 1.1 times 10 to the negative 13th. Gosh, I forgot that number again already. 12th. It's really hard to read on this thing for some reason. Is equal to, and then we've got our Ag plus concentration, which we know is 2.5 times 10 to the negative 4th. The thing here is this 2.5 times 10 to the negative 4th has to be squared because the Ag concentration is squared in our equilibrium expression. Okay, and then we're trying to find the, I guess I'll just leave this CrO4 2 minus. Okay, and that's what we're actually trying to find here. What must the chromate ion concentration be? So, fairly simple algebra here. Should end up with a chromate ion concentration equal to 1.8 times 10 to the negative fifth. Okay, so that's what the concentration must be here, because it's a saturated solution, which means that we are at equilibrium here. Okay, and so that's the idea on that one. Again, not really a lot to the pre-lab or this lab in general. It should be fairly straightforward. So the plan here is we're going to use calcium nitrate and sodium hydroxide, because when those two things react, you're going to have a double replacement. The calcium is going to precipitate with the hydroxide ions, and then we can talk about the equilibrium that exists there. Once that solid forms, we have a saturated solution. We're going to do this as a micro procedure, so you need a 96 well microplate, which we have those, and then we're going to use the pipettes with the capillary tips, and then you get to stir with toothpicks. That's about all you need for the equipment. Let's see, so you're going to do serial dilutions, which you probably did this in biology, where you dilute something by having the concentration, and then you dilute it again by having the concentration, and then you keep doing that. And so the way that this is going to work, it says put 5 drops of the 0.1 molar in well 1, and you want to make sure that the drops are about the same each time, and then you're going to put 5 drops of distilled water in each of the wells 2 through 12. Then you're going to add 5 drops of the 0.1 molar to well 2. It already has 5 drops of distilled water, so that's going to cut your concentration in half, so it'll be 0.05. Then you're going to mix that solution thoroughly, and then you're going to take out the solution from well 2, and you're going to put 5 drops of that solution into well 3, then you're going to put the rest of it back into well 2. You're going to mix. Now, because well 3 already also had 5 drops of water in it, now you're cutting the concentration in half again, and you're going to continue to do this until you get all the way to number 12. So then you're going to have a very dilute solution at that point. So then you're going to determine the concentration of the solution in each well just by calculating it. And so when it says verify here that the concentration is 4.9 times 10 to the negative, gosh, I can't read that number. 4.9, where am I here? 4.9 times 10 to the negative fifth, that's a 5. So when they say verify, all they mean there is just actually do the calculation and check to make sure that they are right. I'm pretty sure that they are, but then we're going to combine it with the sodium hydroxide. So you're going to put 5 drops of the 0.1 into each of the wells there. Okay, and again, you have to remember that as we put in the NaOH, that's going to half all the initial concentrations. Okay, so we're going to keep that in mind. And then you're going to mix those by drawing them up into the pipette, squirting them back into the well. And then that's going to make the concentration of the Ca2 plus ions in the last well 2.4 times 10 to the negative fifth, because it's going to be half what it was before. Okay, and then you're going to give it a few minutes. It takes a few minutes for the precipitates to form here. It says observe the pattern of precipitation. I don't know if they give you a spot to even... yeah, it doesn't really give you a spot to record that data, but they just want you to look at it. At one point, the concentration of both ions becomes too low to have any precipitate form. We're going to assume the first well with no precipitate represents a saturated solution. Okay, so what we're doing here basically is we are cutting the concentration in half, cutting the concentration in half, and we're going to keep doing that until eventually, because of that K, at some point, it's not going to precipitate anymore. Okay, and so the first well that no precipitate forms, we're going to call that a saturated solution. Okay, and then you're going to repeat the procedure. This time you're going to use a serial dilution of the NaOH instead. So you're basically going to start with the other solution and then work your way backwards. But you're doing basically the exact same thing, and again you're going to look for the well where no more precipitate appears. Okay. So fairly simple lab. You should be able to do all of the data collection for that in one day. Really shouldn't take too long. The serial dilutions take a little while, but if you know what you're doing, it'll move pretty fast. So then you're just going to label for the calcium ion serial dilutions the first well with no precipitation, and then for the hydroxide ion, again, the first well with no precipitation, and then figure out the concentrations of both of those in that well, okay, which I guess there are no data tables for this. That's interesting. I would recommend making a data table just to make this easier on yourself. You don't have to. I guess you don't really have to do any of the calculations, honestly, until you figure out which well there's no precipitate in, and then you can figure out what the concentrations are in both those wells. The only thing that's tricky about that is that in this first one up here, the concentration of Ca2+, because we're doing the serial dilution, so you got well 1, 2, 3, 4, 5, 6, all the way up to 12. So let's say that the first time you don't see the precipitate is in well 6. I don't remember exactly when it happens. Okay, but if you start with 0.1 molar here, is it right? Is it 0.1 molar? Yeah. Then that's going to cut in half for the second one. It's going to be 0.05, and then so on and so forth until you get over to well 6. Okay, so then you're going to know what your concentration at well 6 is supposed to be. Then, because you're adding an equal amount of OH minus as the 5 drops that you have in well 6, you have to cut the concentration in half again because you're adding the OH minus to that solution, so that cuts the concentration in half. And then, for the concentration of the OH minus, you're adding 0.1 molar sodium hydroxide in each of the wells. So your concentration of OH minus in each of the wells is going to be 0.05 moles per liter because you're adding 5 drops of that, 5 drops of something else. So, and you didn't do any serial dilutions with the OH minus. So the OH minus is going to be quite a bit more concentrated than the Ca2+. Okay, and then you should be able to, just using the Ksp equation, once you know the concentrations of the Ca2+ and the OH minus in a perfectly saturated solution, you should be able to plug that into your K expression to find your Ksp there. And then you're going to do the same thing again for the hydroxide serial dilution. These two numbers should end up being the same if you do it correctly. I don't know if they tell you to take an average at some point of those. How did the values obtained from the two trials compare with each other? Okay, so they just want you to compare them. Does this method give values that are two? Okay, so once you get done with that, the post-lab calculations kind of explain actually what I just explained, I think. You're going to calculate the concentration of the Ca2+ and OH minus ions in the first well with no precipitate. And then using those concentrations, you're going to determine the solubility. Okay, so really it doesn't give you a lot of explanation, but number one is what I just explained to you as far as the determining the Ksp. Okay, and then you're going to do it again for number 2, and that's going to give you your second Ksp. And then they just want you to compare those two. So once you get those two numbers, you just compare them. And then it says look up the accepted values for the solubility product of calcium hydroxide in the handbook. That should be fairly easy to find online, the Ksp for calcium hydroxide, and then compare that to your values. And then you're going to decide whether this method gives values that are too low or too high. Okay, so here, again, without completely answering this question, because it's a good question, let's say that your the first time you see no precipitate is in well number 5. Okay, so you've got a precipitate here, you've got a precipitate here, you've got a precipitate here, you've got a precipitate here. Once you get to 5, your concentrations actually might be a little bit lower than they are in an actually saturated solution. Okay, so then you got to think about if the concentrations we're plugging into the Ksp expression are a little bit lower than they should be, then what's that going to do to the values of your Ksp? Alright, and hopefully that's a good enough hint that you can figure it out. What would make the method more accurate? Number 5, you guys can talk, or think about what would help make this method more accurate maybe. would the results be better if the concentrations of the last well where precipitation occurred were averaged with the first well where there was no precipitate? In other words, taking this one right here and averaging the two of these, the last one with the precipitate with the first one where there's no precipitate. Is there any justification for doing that? Well, I feel like, okay, so I tell you what, figure out a way to answer number 5 that is not number 6, because number 6, they kind of suggest maybe a way to help make it more accurate, but see if you can come up with another way besides the one that they give you there, okay? Just to make it a little bit harder on that post-lab. Is that it? I think that might be it. Okay, so that's it for that lab. Not really a difficult lab either to do or really to do the post-lab for, so this one should be pretty straightforward. I guess we'll see you guys in class. Have a good weekend.